And we got to stop it there. Oh, just getting good. That's okay. Today's going to be just as awesome. Good morning, everybody. Today, we tackle a whole new, I was going to say branch of mathematics, but that's not quite true. Not exactly a branch of mathematics, although you could call it that, the study of. He said, whole new type of numbers. That is complex numbers. You read about them this weekend, hopefully, took notes from the textbook. It does an okay job. It's not bad. But the textbook version is boring. It's terrible. It's like, okay, here's this thing. We call it an imaginary number. Here's how it works. Like, okay, that's great. But why? Right? Where do they come from? Why are they called imaginary in the first place? What are they good for? How the heck am I supposed to think about this? I've got regular numbers and integers and then all the fractions and the decimals that are actually just a different way of writing fractions. And then we had negative numbers thrown into the mix. Oh my gosh, that really threw people for a loop. Historically speaking, people freaked out about negative numbers. And that's what we're going to start with today, because people freaked out about imaginary numbers. But you didn't know that. That's why they're called imaginary. So this site, before I get into it, let me introduce. This site, betterexplained.com. It's a fantastic website, one of my top favorites ever, because it does exactly what it says. It explains math better. I thought I knew imaginary numbers. I thought, okay, I get them, they're a thing, and then I read this, and I was like, oh, that's how they work? It's really just, it's so simple. It is, seriously, visual, intuitive guide to imaginary numbers. I kid you not. This thing works. This guy is a genius. So I'm going to start you here rather than leave you to wait until you're like halfway done with college to finally see this, okay? Like I had to do, because it's wonderful. And you can go back to this website for just about anything. He doesn't hit a lot of the low-end stuff. It's mainly geared towards calculus and maybe like pre-calc kind of topics. So you might not find every little thing you're looking for this year. But a lot of the big picture stuff we'll see this year, you could find on this site. He does a good job. Anyways, let's get into it. Follow along with me. Take some notes. Write some of this stuff down, because it's good stuff. Here we have a table. And here we're comparing complex numbers to negative numbers, because that's historically exactly what happened. We had numbers. We had the counting numbers, 1, 2, 3, 4, 5. Somewhere along the line, they decided to throw 0 into the mix. They're like, hey, wouldn't it be great if we could actually write something down, even when we mean nothing, so that you know we didn't just accidentally leave a space? Yeah, that's probably a good idea. Let's make a number 0. Okay, then we get the integers. And integers weren't good enough for everything because fractions exist. So we had to have fractions, and you get all little bits in between all the integers. And then along came negative numbers. And it came about like this. Well, what happens if you said, what is 3 minus 4? How can you have less than nothing? And they were like, but you can't have less than nothing. That doesn't make any sense. And then the bankers come along and be like, you think you have $500, but you actually owe me $600. So really what you have is a debt of $100. You don't really have money. You have debt. That's the opposite of having money. And then everybody's like, oh, yeah, that's a good point. Okay, maybe we can call negative numbers the opposite of numbers, right? And so what we get is this reversal effect that multiplying by a negative, when you apply that multiplicatively, because that's multiplication, the most important operation from here forward. Addition, subtraction, meh. Multiplication, the big deal, right? That's the most important one. So when you multiply by a negative, what happens? Notice there, it goes from positive to negative, and then positive to negative. It flip-flops back and forth, right? Every time you multiply by a negative again, This is why we say two negatives make a positive. Negative times a negative, right? If you start out negative and then you multiply another negative, you get back to positive. And the visual part comes in that number line. If you imagine the number line from 0 going forward to positive infinity, negative means flip, reverse, go backwards. That was great. And then later on, somebody asked this stupid question. Okay, I like my negative numbers. I also really like square rooting stuff. Can I square root a negative number? Right? Can you imagine the class where that happened in? Some kid raises his hand. What's the square root of -1? Haha, got you now, teacher. Like, what, you can't do that. And for the longest time, that's what it was. You can't do that. You just can't. Not allowed. You broke it. It's like dividing by 0. No touchy. But then somebody had the bright idea, well, okay, I know we really can't. Like, we're not supposed to, but what if we did anyways? That's what mathematicians like to do in their free time. They find the rules that say you can't do something and go, I'm going to do it anyway. Right? This is why teenagers would make excellent mathematicians, because the teenager looks at a sign that says do not touch, and the first impulse, what do they want to do? Touch it. Touch it. Right? Do not take the square root of -1. I'm going to do it anyway. See what happens. And they thought he was crazy. They said, dude, you're insane. You're just like inventing these things that you say work with square roots of negatives. That's preposterous. Those aren't real numbers. You're clearly in imaginary land, all right? Imaginary numbers. And that's why they called them imaginary numbers. It was a derogative term. It was to make fun of them. Pathetic numbers. You're not even real. And then it turns out they're incredibly useful. Because if the negative number was a flip from positive to reverse direction instantaneously, the complex numbers, the imaginary numbers, say, what if I didn't want to do that all at once? Right? The square root of -1 says, we'll get back to the rest of the table here. How can you have less than nothing? Enter imaginary numbers. How can I have a number squared to give me a negative? Generalize that. How can I take a thing, operate on it twice? I want to do to it something twice. Remember, there's an invisible 1 in front of this. So it's not just x squared. It's 1 times x times x. Right? That's what squared means. Multiply by x twice. Something called imaginary numbers. Let's pretend they can exist. They do. They're just as real. They just got this derogatory term. So let's accept this as possible. We have a thing called I that if you did it twice, if you multiplied by I twice, that's the same as multiplying by -1. So go back to the number line. What can we possibly do on the number line that 2 steps would get us reversed? The answer is rotate. What we do is we add an additional axis. We say we'll call that imaginary. So 1i is over here. And multiplying by I rotates the number. Right? Multiplying by the negative flips it around. You go from here, instantly there. Multiplying by I gives me a half step. I'm halfway there. I haven't quite flipped over. Multiply another I. You go all the way. Multiplying by I is a rotation. The imaginary numbers are another dimension of numbers. It's slightly more complicated than negatives. Negatives said numbers can go in another direction. Technically didn't add a dimension. It was still along the same line. Negative numbers added another direction. Imaginary numbers add another dimension. This is not our Cartesian plane. This is not x and y. This is real number line, imaginary number line. They can also go positive 1, 2, 3i, negative I, negative 2i, negative 3i. Right? So I could multiply by negative I, and then I flip in the other direction. Instead of rotating counterclockwise, I rotate clockwise. And I end up down here. So really the first thing you must accept to truly understand imaginary numbers is, number one, numbers themselves, the real numbers. What was it? What does 1 mean? You're dealing with advanced mathematics now. It is no longer enough to think of 1 as representing an item. This is not 1. This is not 2. This is not 3. I do not have 3 objects. 3 is not a counting of things. That's not good enough anymore. You need to update your model. 3 now means a distance from 0. Every number, back to the number line, distance from 0. 1, 2, 3. Now that we've added negative to it, we've added an opposite. I can be 3 in this way. I can be 3 that way. So really, a positive real number is not just amount from 0, it's also a direction. In your brains, right now, from this point forward, I want you to think of every number you encounter as a distance and a direction from 0. This will help you. Guarantee so much if you can start that process now. Every number is a distance and a direction from 0. Positive real numbers go this way. Negative real numbers go that way. Imaginary numbers are perpendicular. They go up and down. Positive I, negative I. It's the same distance. 1i is the same distance as positive 1, regular old 1. I and 1 are the same distance from 0. Right? I could draw a circle around there. It would be equally spaced from 0. It's just a matter of which direction did I go in. And this leads us to, right? As I said, numbers are two-dimensional. And so a complex number, well, hang on, I'll get to the full complex number. I want to talk about the pattern first. Multiplying by negative 1. Take a 1. Start multiplying by negative. Repeat, repeat, repeat. Positive 1, negative 1. Positive 1, negative 1. Right? It flips back and forth. Alternates. One and the other. Look what happens when I multiply by I. I squared, I cubed, I to the 4th, I to the 5th, right? We keep multiplying by I. No i's, you're just left with 1. 1 I, obviously, I, okay? Nothing fancy yet. I squared gets you back to negative 1. That was what started all this. Now what about I cubed? I cubed is I times I times I. Well, the two of them together, that made negative 1. And now I have 1 left over, so it's negative 1 times I. Negative I. 3 rotations, sorry, this way, 2, my elbow don't go that way, 3. And we end up back down here at the bottom, right? 1 I around, 2 I's around, 3 I's, now we're down here in the negative I direction. And then times 4, a 4th I rotates it again. Every multiplication by I rotates 90 degrees counterclockwise, or a quarter of a circle. Pi over 2, if you prefer the radians, which you should. with me so far? Okay. Questions from Zoom? All right. Then, here's where things get complicated. Technically, complex, right? Literally, that's what we call it, complex. When we have a real part and an imaginary part, it's complex. Really, every number now is complex. Plain old 3 is actually not just a real number, it is a complex number. It's just 3 plus 0i. Right? Every number can be represented as a distance from 0 in this direction plus a distance from 0 in that dimension. Right? Just like every point on the plane can be represented by x, y coordinates. We're taking good old Cartesian coordinates, and instead of saying this is x, this is y, they're both real, say, it's a location in the complex plane. How much real plus how much imaginary? 1 plus I is the same as the coordinate 1, 1 on your xy plane. Every number is two-dimensional now. 1 plus I says quite literally this much real and this much imaginary, but it also represents this final vector. That whole distance, you know, that's more than 1 away, right? I've added two things together. I've added a positive quantity and a positive quantity. I haven't taken away. I should end up more than 1 away from 0. Notice that this diagonal reaches past wherever a circle would end up here. I apologize to those on Zoom. I only have whiteboard. I should have exported the web file into Notability so I could draw on it, right? But if this was a circle of radius 1, right, every point on this circle is distance 1 from 0. 1 plus I is farther away than that. But it's not 2 away. Right? Think back to geometry. This is a 45, 45, 90 triangle. This is 1, this is 1. This hypotenuse would be Pythagorean Theorem. 1 squared plus 1 squared is 1, so square root of that. Square root of 2, right? Which is more than 1, but less than 2. More than 1, it goes past here, but it's less than 2, which would be, I guess, further out, right? 1 plus I is a distance of square root 2 away from 0, 45 degrees into the imaginary dimension. That's the most complicated part so far. You don't quite need this bit yet. If this next step of visualizing complex numbers as a point on the complex plane is a little too far for you, don't fret that bit yet. That part's not critical. The critical part is every multiplication of I is a quarter turn around. That will help you. When you see, I to the 57th power, what does that reduce to? Well, it's very easy. That's 57 turns. Every 4 turns I get back to 1. So really I need to find the next place where 57, that's actually how many past a multiple of 4. Let's go one less. Is 56 a multiple of 4? You sure? 50 and 6. Half of 50 is 25. Half of 6 is 3. 25 plus 3 is 28. So half of 56 is 28. Can I take half of 28 again? Yes, I can. 56 is a multiple of 4. So 56 i's. I to the 56th power ends up right back here at positive 1. I to the 57th, one more. That's how you simplify I to the many powers. Right? Find out how many turns past 1 is it actually. That's all you need. And then the other thing is the actual arithmetic, which we will practice tomorrow. Okay, I give you a complex number, 1 plus I. And I say, okay, add to that 3 plus 4i. It's just combining like terms. Real parts combined with real parts. Imaginary parts combined with imaginary parts. 1 plus I plus, what did I say, 3 plus 4i? That's right, would be 4 plus 5i, whatever. Add them separately. Right? Any number, some amount, I should have started with this, right? Some amount in the real dimension plus some amount in the imaginary dimension gives us our coordinates in the complex plane. That's all they are. And so the size, right? How far away, this is what I was saying earlier, right? Distance formula, aka Pythagorean Theorem, tells you how big that complex number really is. Probably won't be calculating that yet, but it's good to know. But that's why they are just the same. So think of every number as a distance from 0 in a particular direction. And so with the complex numbers, distance formula to find that distance. It's a Pythagorean theorem. Okay. Easy enough. Now, of course, to find the particular direction, you'd have to calculate that angle. That requires some trigonometry. We'll get to that later in the year. Let's see an example of this in real life. These are actually used, or at least this is one method that is actually used for calculating the heading, the direction we're traveling, usually nautical. Could be aeronautical as well, so boats, planes. Right. Find the heading. I was going this direction. I'm on a boat heading 3 units east for every 4 units north. 3, 4, that's our triangle. I'm going that way. That's my rise over run, right? My slope, as it were. And then I want to change my heading by 45 degrees counterclockwise. What's my new heading? That's a good question. That's a tricky question to answer, because you gotta like break this down into components and this is that angle, and then I add that angle, and then we combine the angles, and now I get the new components, and oof. Yeah, take the sine, the cosine, the Glaber group by the tangent, flux and foobar. It's a trig mess. Or it's a complex number, walk in the park. Here we go. 3 in one direction, 4 in the other. That's just 3 plus 4i. I don't care what the angle is. Rotate by 45 degrees. 45 degrees is 1 plus I. That perfect diagonal. So I've taken 3 plus 4i. Multiply means to rotate it. I want to rotate, so I'm going to multiply it. 3 plus 4i times 1 plus I. I'm literally multiplying those two numbers. That's it. Multiply two binomials. Hey, where have we practiced that before? Right? Isn't this a binomial? This is a thing plus another thing. They can't quite combine because they're not like terms. Times another binomial. Dish that out. 3 times 1 is 3. We'll do the ends a bit. 4i times I is It's 4i squared, and I squared really is -1. So even though right now it looks like positive 4i squared, I squared says, I squared is -1. So it's really a -4, right? Add that to my 3. I had positive 3. Now I get -4. 3 plus -4 is -1. That's my real part. So the squared bits on the ends, right? Real times real, you'll get a real part. Imaginary times imaginary. The two i's multiply together give you a -1. Two imaginaries multiplied give you another real component. Net result, -1 in the real direction. And then we have the two center parts. We have 3 times positive I plus 4i times 1. So that's 3i plus 4i, or 7i total. Look at that result. This thing got massive, didn't it? All I wanted to do was, I'm going this far, I want to rotate 45 degrees. Ideally, it should be the same distance from 0, right? But it's not. That's okay, because all we're concerned about is the direction, right? If I had to reduce this down to be the same length as that one, I could do that. But then I wouldn't get a nice, clean integer numbers, right? I wouldn't have 1 and 7. It'd have to be like 0.7589 plus 5.2i or something, right? Something like that. See the difference there? So don't be freaked out that the arrow got longer. Wait, I'm now further away. Oh no. I was only asking about the direction. So if all you care about is the direction, you know the distance. Really, if this is a vector representing your traversal, the length of the arrow will represent speed. The faster you go, the longer the arrow is. After you make your turn, you're still going to go the same speed. You still have your boat set to, Mach 5, whatever. That's way too fast. Right? Oh, look, they did the math for us. How convenient. Isn't that neat? No trig required. Whoopee! I know, you guys haven't actually studied the trig part yet, so you don't know how wonderful it is to just avoid. But it's kind of nice. Wait, that's really simple. Now the trig's going to come in and make it complicated. But the trig has its uses too. Don't worry. Also, you can do that if you don't have the scientific calculator handy. What if there's no sine or cosine button, right? You'd be screwed. Not with complex numbers. All right. Complex numbers aren't. They aren't complex. Not that big of an idea. Still strange. Absolutely. But first recognize that 0 itself was weird to start writing down for people. Negative numbers freaked people out. Imaginary numbers freaked people out so much they insulted them by saying they weren't real and calling them imaginary. But they're very real, very useful. In fact, it doesn't get into it on this page, but the number one application of complex numbers that I can think of has to do with electronic circuits. So, you have a phone, yes? Everybody has one now. This thing cannot exist without complex numbers. in order to do the math on the circuits involved, right, the electrons flowing through the wires across the circuit board, get from here to there, and it has to pass through this component, past that thing, up to the next one. In order to do that in such a way that it doesn't all burst into flame, the only model we have that can do the calculations accurately is complex numbers. Complex numbers make your cell phone possible and every other electronic device. Right? This is one of those cases where it started out purely theoretical, like, hey, this is a neat bit of mathematics, and then somebody came along and said, hey, I'm trying to figure out the equations for this thing to model the electrons flowing in a circuit diagram, but like, I need an operation that has four-fold symmetry. Can you have a thing where like I do it 4 times and I get back to the same result? And somebody said, hey, imaginary numbers do that. I bet they'd be useful for you. And he goes, oh, hey, yeah, that works pretty well. So that's what they used. And it turns out it made the calculations quite simple. Even, I wouldn't say as simple as this, but it's not just ignoring trig, but it's like you have to model it as complex numbers. It's the only way it makes any sense. The only way you can do the calculation. So, very necessary component. And the final bit I will leave you with is this. We'll look at this more on, I think Tuesday or Wednesday. I'll check. But do you remember parabolas? Quadratic equations. Remember how we said, well, it's always supposed to have 2 zeros, 2 roots, right? Oh, but what if like I have an upward facing parabola and I shift it up so high it never crosses the x-axis? Where are the roots now? Where do you think they went? They didn't cease to exist. They just shifted into another dimension. Every parabola has 2 complex roots. It's just that sometimes we get lucky and the complex numbers have 0 in the imaginary direction and they can be represented by real numbers. Right? Because remember, every real number is also a complex number. So if I tell you every parabola has 2 complex roots, sometimes those complex roots are also real roots. So that's what we're going to look at next, is solving them and say, hey, okay, now I can take the square root of a negative number, right? I told you we'd get back to the beginning here. The quadratic formula, x is equal to opposite of b plus or minus the square root of b squared. Okay, if I square a number, that's always positive, right? If b was positive, positive times positive, positive. If b started out negative, negative times negative, still positive. So b squared is always positive. Minus 4ac. What if 4 times a times c is bigger than b squared? I can't take the square root of a negative. That's why we called that number in there. Remember what it was called? B squared minus 4ac. We had a term for that. Determinant, because it determines whether or not you're going to have real roots or complex roots. Because if it ends up negative, you're now taking the square root of a negative. You're going to get a complex answer. That's okay. Now, we can deal with that. We have the tools, the technology. Weird to think about math as a form of technology. It is. Complex numbers, that's new math technology. Considered absurd until, I would agree with this. Like mathematicians have accepted it in the past 100 years or so, but the general public still thinks they're ridiculous. They're not. Spread the word. Complex numbers are okay. Imaginary numbers are real numbers too. Right? They have feelings. Stop insulting them. The name's stuck, though. We can't change that, unfortunately. We just have to convince people that imagination is still valuable. Right? Then maybe they'll accept it. I don't know. All right, that's all I've got for today. At this point, I'm rambling. I apologize. I asked you to jot down some notes. There's some good stuff on here. Use that visual representation, that diagram. Right? That guy, boom, yeah, have that as a reference. And probably the generic one, maybe stick that, right? There's your representation for the day. If I had to pick today into one picture, that'd be it. Put that diagram in your notes, okay? Upload a picture of your notes to Google Classroom for today, just to check in. Hey, I was here, I was listening, I was paying attention, I did the thing. That's all I've got for you. The practice, yes, now I remember, right? So tomorrow we will be practicing the arithmetic. We'll be adding, subtracting, multiplying, and dividing complex numbers. And then once we've got that, a handle on that, Wednesday, we'll go back to the quadratic formula and getting complex solutions. Fun times. All right. So if there are no further questions, I will end the stream here.